This is Lab 5, Choose Your Own Adventure. The Law of Conservation of Energy in the Bounce of a Basketball. My objective was to show the conservation of energy in the bounce of a basketball. To do this, I used Newton's second law, which states that force is equal to mass times acceleration. Newton's second law was used to model the motion of the ball. The other principle I used was the energy principle, which states that the change in energy is equal to the change in work plus change in internal energy, which is found when the ball hits the ground. The law of conservation of energy states that energy cannot be created or destroyed, but only changed from one form into another or transferred from one object to another. I found in my results that this is true because energy is transferred into internal energy when the ball bounces and compresses against the floor. Therefore, energy is conserved. Here is the video that I used to make my model. To go into more detail about the concepts I used, for Newton's second law, I know that the system only consists of the ball and the earth, so the only force acting on the ball is the force of gravity. I also used Newton's second law to calculate the acceleration, which is net force divided by mass, which I then used to calculate the velocity changes of the ball during the bounce. In order to properly model the bounce of the ball and calculate energy, I used the energy principle, setting work equal to net force times the position of the ball on the y-axis. I also set the change in internal energy equal to the negative change in work because there is no energy transfer into the system. It's just converted into internal energy. This code shows my initial data. I set the mass equal to the mass of a basketball, which I found online, and I used the initial position data I retrieved from Tracker. I set g equal to the gravitational constant, 9.8, and I set the j hat vector to the positive y direction. Here, I use these equations to find the kinetic energy and gravitational potential energy of the ball, which I then use later to find the internal energy. In the while loop, the data associated with the ball is updated as it moves. As mentioned before, the net force is equal to the force of gravity acting on the ball. Here, I account for the bounce of the ball when it hits the ground. This changes the velocity from being in the negative y direction to the positive y direction. I then calculate the work as net force times the ball position. I also found the internal energy using the energy principle by subtracting the change in kinetic and potential energies from the work. From there, I found the new velocity of the ball. Here is the output when I run the model. This graph shows the changes in energies during the bounce. The blue shows the kinetic energy, the red shows the potential energy, and the green is the total energy, which remains constant throughout the motion. This graph shows the position versus time graph, which very closely resembles the model that was generated by the data from Tracker, right here. My model shows the law of energy conservation applies to the bounce of a basketball. One thing that this model does not show is the loss of energy when the ball is compressed on the floor. This energy loss can be a transfer of heat energy, sound energy, or vibrational energy. Even with this transfer of energy, the model still accurately shows that the total energy does not change during the bounce.